In this video, we discuss how to trace the pH curve of a titration in which we are going to analyze a weak base, in this case ammonia. We're going to titrate it with a strong acid, which will be hydrochloric acid. Right, so this is our titration. Here as an analyte, we have a solution of ammonia, 0.1 molar, and we have 20 mL of that solution. And then we're going to titrate it with a strong acid, hydrochloric acid, which is in 0.1 molar concentration. The goal of this exercise is to see how the pH changes upon addition of the strong acid. All right, the first thing to consider here is the reaction that takes place between the weak base and the strong acid. Right, so that is the weak base, ammonia, which you're going to react with the strong acid, hydrochloric acid, to generate the conjugate acid of the base, ammonium, and then chloride ions. Okay, so that is the reaction at play during titration. And again, the goal is to try to see how this reaction changes the pH in the flask as you move from no volume of acid added to an infinite volume of acid added. Okay, so we're going to start with no hydrochloric acid, and then we will add 10 mL of hydrochloric acid, 20, and then 30. Alright, so let's start at the beginning of the titration when there is no acid and there's only weak base. Alright, because you have a weak base, then the pH is calculated using the equilibrium constant of the base, which requires use of an ice diagram. Alright, so we have here the equilibrium for the base is going to be this. Okay, that is what happens when you don't have any acid and only the weak base. And then you just have to write here what the ice diagram looks like. Your initial concentration for the base is 0.1 molar, and then you have no conjugate acid and no hydroxide. The change will be minus x plus x plus x. And then at equilibrium you will have 0.1 minus x, x and x. And with these values at equilibrium, then you can go to the equilibrium constant and figure out what the concentration of hydroxide is. Right? K sub B will be the concentration of ammonium ions plus the concentration of hydroxide over the concentration of the base. And this is equal to x squared over 0.1 minus x. And this value of the equilibrium constant is equal to 1.8 10 to the minus 5, okay, which is given by the problem. Alright, so there you have a quadratic expression that you can solve using the approximation method to find that this x, which is exactly the same as the concentration of hydroxide, is equal to 1.3 10 to the minus 3 molar. From here you can calculate the pOH, and then 14 minus the pOH will be the pH, which in this particular case is 11.11. So that is the first point in our titration curve. At the start of the titration, when no acid has been added, then we have a pH that is basic, as you expect, and that pH happens to be 11.11 in this particular exercise. Let's move on to the second point in the titration, when we add 10 mL of the acid. Now, something that is important about this point is that this is what we call the half-equivalence point. Notice that 10 mL of the acid is exactly half the moles as what you have of the base. And we're going to substantiate that by simply writing here the number of moles before reaction and then after reaction. Okay, so the first row here will be the numbers of moles of each component before the acid-base reaction takes place, and then after the reaction has taken place. Right, so before, the number of moles of ammonia will be the concentration times the volume, which is 2.00 10 to the minus 3 moles. And then for this particular point in the titration, you will have 10 mL of 0.1 molar hydrochloric acid, and the moles of that is 1.00 10 to the minus 3, also in moles. And you have nothing of the products. Okay, but after the reaction takes place, we can see that, well, hydrochloric acid is the limiting reagent, so there will be nothing left over. And the amount of ammonium will be 1.00 10 to the minus 3. We also will have some chloride, but that is irrelevant to the acid-base calculations. and then there is 1.0010 to the minus 3 mole left behind of the weak base. Right, so this is what we call a buffer, where you have equal concentrations of weak base and its conjugate acid. And for buffers, the pH can be easily calculated using the Henderson-Hasselbalch equation. Now, something that is important about this case is that this is a base equilibrium, and the Henderson-Hasselbalch equation that you have to use is that corresponds to the base equilibrium, right? So that will be POH is equal to the pK sub B of that equilibrium plus the logarithm of the molar concentration of the conjugate acid over the base. Because both the conjugate acid and the base are in the same volume, then this applies also to the number of moles. Okay, and because the number of moles of the conjugate acid is identical to the number of moles of the base, then this ratio is equal to 1, and the logarithm of 1 is 0, which means that at exactly half the equivalence point, then you have that the POH is equal to the pK sub B. So the only thing that you have to do is then take the minus based on logarithm of this number to obtain what the POH will be, 4.74, and then you'd take 14, subtract this number to get the pH. And the pH then at the equivalence point happens to be, at the half equivalence point happens to be 9.26. Okay, that is, the half equivalence point is an easy point to calculate because the pH is dictated by the Henderson-Hasselbalch equation. Right, so this makes perfect sense. We have added some acid and the pH has dropped. That's exactly what we expect. Let's now move to the equivalence point. Okay, so in the equivalence point, what happens is that now you add exactly the same amount of acid as you have of base, and what that means is that the reaction is stoichiometric. Right, so there's no base left over, and then there's no acid left over. But something that is important is that now you have 2 moles of the conjugate acid in solution. And the conjugate acid has acid-base properties, right? The conjugate acid by itself has the following chemistry. This ammonium can react with, can dissociate to generate ammonia plus protons. All right, so the generation of those protons is going to make the pH acidic, even though we are at the equivalence point in the acid-base titration. Right? To figure out exactly how the pH works, or what the pH is at the equivalence point, then what we'll have to do is set up an ice diagram and then calculate the pH from there. Right, so for the ice diagram, we have 2 moles of ammonium ions, and then the volume that we have will be 20 mils of the acid and 20 mils of the base. That would be 40 mils. All right, so that would be your concentration, which happens to be 5.0010 to the minus 2. Initially you have no base and then no protons. The change will be minus x plus x plus x, and then at equilibrium you will have 5.0010 to the minus 2 minus x, x and x. Right, so we're ready then to go to the equilibrium constant and calculate what the concentration of protons is. Notice that this is now an acid process whose equilibrium constant will be the water autodissociation constant over the basic constant for ammonia. Okay, and that is going to be equal to 5.6 10 to the minus 10. And that is equal to the concentration of ammonia times protons over ammonium at equilibrium. Okay, so there you have another quadratic equation that you can solve using an approximation, okay, where you neglect this x with respect to 0.05 to find that this x, which is the concentration of protons at equilibrium in the equivalence point, that x happens to be 5.3 10 to the minus 6. Okay, that means that the pH at the equivalence point happens to be 5.28. Alright, so at the equivalence point, when you have added exactly the same number of moles of acid as you had of base, okay, you actually have a pH that is not neutral. And the reason is that because you're titrating a weak base, you're generating a conjugate acid that can undergo some secondary chemistry changing the pH. Okay, so that is something that is expected, and those are the actual numbers that we have right here. Right, so let's try to wrap up this video by calculating what happens when you add even more acid. Okay, so now we're past the equivalence point, and we have added 30 mils of hydrochloric acid. So we go to our stoichiometric calculations, and you will have that this is what you have added. So there's no leftover of the base, and then there's 1.00 10 to the minus 3 moles left over of hydrochloric acid. Okay, and then there will be 2 moles of the ammonium chloride. Okay, now this can do some chemistry, but that chemistry is going to be completely overwhelmed by the acidity of this leftover acid. So all of the pH calculations solely consider that numbers of excess acid that you have right there. Okay, the calculation then is going to be straightforward. You will have that the concentration of protons is simply going to be the number of moles over the volume. The number of moles will be 1.00 10 to the minus 3. And then the volume will be 30 mils plus 20 that you had initially is going to be equal to 50 mils. Okay? So that is going to give you a concentration of 0.02 molar. And then the pH from that, you just take the minus based on logarithm of that number, and then you get 1.699, where you have 3 significant figures. Okay? Alright, so clearly the pH continues to drop, and it does so very steeply once you get past the equivalence point. Right, we can just finish this video by considering what the pH would be if you added an infinite amount of acid. And if you have an infinite amount of acid, then the pH will be the pH of the acid. Right, the concentration of hydrochloric acid is 0.1 molar. That means that the pH at infinite volume would be 1. Right, so that is the end of your weak base with strong acid titration. We have calculated 4 points. The initial point that requires a nice diagram for the base alone. Then we have half the equivalence point, which can be solved with the Henderson-Hasselbalch equation because you have a buffer. Then we have the equivalence point, for which you have to look at the secondary chemistry of the conjugate acid. And then we have excess acid, which is fairly trivial. That is just the amount of excess acid that you have left over. Okay, so this video completes a series of 3 where we have looked at acid-base titrations of a strong acid with a strong base, a weak acid with a strong base, and here a weak base with a strong acid.